where, you know, we have a lot of research analysts doing a lot of ground research with meeting clients and companies. Now suddenly everything has gone virtual. So most of the head office guys mailboxes are flooded with, you know, normal mails like attachment sent or a link for Zoom, so and so. So instead of, you know, going through each and every mail and acknowledging them like, okay, received, thanks, or sorry, or I'll be delayed, or those kind of things, they wanted, so they came back to the AI team saying, see, I get, you know, maybe 400, 500 emails now from various stakeholders, companies or teams, asking me for approvals, asking me for joining meetings, asking me for acknowledgements and those kind of things. So is there any way in which, you know, you can understand the context of the sender and then kind of send out a bot generated replies, automated replies? So which is what actually, if you think of it, this is what Gmail does right now. So when, you know, when you try to reply back to an email saying hi, it will automatically prompt the name of the name of the person whom you are addressing the mail to. Or maybe again, you know, a lot of autocompletes is like sentences are generated. Like when I say thanks for something, something, or if there is an attachment, then again, you know, that attachment word is very promptly visible there. So something of those things, which you know, this is where this AI powered auto generation text generators are coming in handy nowadays. And that's why I just wanted to, since we have been working on this, so I wanted to take up this very interesting topic. Okay, so this is about me. So I work in NLP basically. So that's why, you know, I deal with a lot of text generation and natural language processing. You can always connect me on my Twitter handle, which is fuzzymind1. And this is how basically we'll go today. We'll quickly see an introduction to neural networks that forms the basis of all these text generation algorithms. And we will see the shortcoming of our recurrent neural networks. Then we will jump into this long short-term memory. It's a very ironical name, saying long short-term memory. And we'll see a demo. In between also, you know, we will see a lot of small working demos, interesting concepts, you know, so we'll try to keep it moving, not just algorithms and diagrams. All right. So yeah, so why do we need, I'll just move this style, right? So why do we need an auto text generation? So as I was mentioning earlier that, you know, for sentence completion as in emails, for image caption generator. So you have a lot of billboards and ads these days, Google ads and ad campaigns for brands, for cars especially. So every time when you see a picture, you don't expect an actual human interpreter to caption that image. So there are AI algorithms which actually generate very interesting image captions. And that is a very, you know, booming industry, booming business, having image caption generator, automated image caption generator. Then again, you know, to automate mundane responses to messages like received or thanks or sorry or delayed, those kind of things, right? Then even in publishing industry, where, you know, you have to write prologues or you have to summarize few text, epilogues and those things which are pretty, you know, rudimentary tasks or run of the mill tasks. So for those things also, having some bot to automate these things so that you can maybe concentrate on more productive things. So that comes in handy. Also, brand powerhouses like Toyota, for example, they are using these AI generators, AI powered text generators to create whole ad campaigns or even brand slogans. Now, if you see that, you know, just being creative is not the way. You have to be innovative as well. You have to capture a wide variety of audience and open up a wide vista of imagination for your target audience, which is where, you know, the campaign needs to be very diverse. It needs to be very how should I say, kind of, you know, eye catching. So for all these kind of things, we are increasingly using LSTMs for these things, and training bots wherein, you know, your bots will reply on your behalf. I would like to show you Toyota's ad campaign here. I'm just going to minimize my screen. Okay, and we will see Toyota's ad campaign here, and you can see the power of, yep, you can see the power of these. So what actually, a bit of background. So what happened was IBM Watson, which is the AI engine for IBM, that was fed over 1,000 different activities like kayaking, biking, cycling, dancing, singing, whatever. And then they had to pair any two activities which are, they have the least probability of being matched together. For example, maybe reading, writing, singing, yes, but what about barbecue and surfing? Something of those sort, which are totally diametrically opposite thing. And the algorithm actually, came up with various, I mean, interesting combinations and also named them. We will see how it named them and what those ad campaigns look like. So this is the ad for Toyota brand, okay, and this is how they are positioning it. Okay, so identified martial arts. So one of the activity identified was martial arts. Okay, and it was pairing it with, let us see what it pairs it with. Okay, it is pairing it with barbecue. All right, and then it is coming up with the name. You should try Taekwondo tenderizer. See, and then it is also giving a description for that tenderized piece of meat for your backyard BBQ using so and so. So just imagine, this is what an AI is doing. It is taking in information, it is combining that information, and it is coming out with some piece which is totally interesting, totally out of this world. So this is the power of neural networks and machine learning. Oh, sorry. I think I have, sorry. Yeah, sorry for this. So this is how they are being, utilized. And this is one of the ad campaigns. Like this, Toyota has unleashed a campaign of about 6 or 8 ads, which are, based on various innovative ideas. So this was one where, it was trying to pair two different activities, outdoor activities, indoor activities. There's another where it is trying to club in Halloween names together and come up with some, different unique Halloween theme. So these kind of things. So even text generators are employed for in the music industry for auto generating poems, for correcting the rhyme scheme. So maybe if you have a paragraph and the end words don't rhyme that much, or the rhyme scheme is off a bit, so they are even used in that kind of scenario. A lot of applications for them. Okay, so how does auto text generation work? So basically, for any task where you have to feed in humongous amounts of data and then use the past to make a prediction about the future, this is where machine learning steps in. So you're going to prepare your data, which is going to feed loads of data. Then we have to make sure that the data is rich and from a variety of sources, so that one component is not underrepresented or one component is not overrepresented. We clean and label the data, and we feed the data to our robot, which is our machine learning algorithm. We train the algorithm, we test it, we evaluate it by using it in some practical scenario, and then depending on the prediction whether it is close to what we expect or not, we revise our algorithm, tune some parameters and stuff. So the final conclusion of all these steps is we are using supervised learning. I mean, simply put, what we are doing is we are using supervised learning. So you are supervising the steps, the learning of the algorithm, and then correcting it if it is trying to give unpredictable results. All right, and just this point brings me to a very interesting idea. So this slide, even for this slide, this was not all these diagrams were not input by me. This was suggested to me by the design ideas. So imagine that it took the context of what I was telling it. So I never had all these prepare and data and clean and label steps and stuff. I just had these steps, and taking into account the context of these steps, it suggested me design ideas, and I mean actually came out with a very decent nice looking slide. So yeah, I mean, this is also one of the applications of text generation. Now coming back, whenever we talk of text generators, machine learning algorithms in this kind of scenario where you have to learn from something. So that is where, you know, neural network comes in. As soon as when we say that from past I have to extrapolate and do something, especially with related to natural language, like speech or voice, we immediately start putting in algorithms that can replicate our brain signals. Okay, so this is how the brain neurons work, and this is why we have the name neural networks. Okay, basically what the diagram represents is you have inputs, okay, then you have some kind of operations on those inputs, and you have an output. Now don't get all overwhelmed by the fancy symbols of what are the crosses doing and what are the addition doing and stuff like that. It is very simple. So whenever you have inputs from a variety of sources, you will always have some weights attached to the inputs. For example, maybe some input might be given more predominance, some input is not that important in making decision. So we'll always attach weights to those inputs. These x's are nothing but the weights which are attached. This is something which is the bias. Bias meaning that I am 100% this is not the correct thing, right? Weights are something which I by way of learning I assign some weights. So I also put in some bias as a correction mechanism. So this is nothing but multiplying the weights, adding a bias, okay, and then giving out the output. Output is nothing but a prediction. It is something of a percentage or a probabilistic output. So this is what we do when we talk of neural networks. So this is, I was explaining that each input is multiplied by a weight, just signifying that how much importance to give to each input, and they are summed up with the bias. And what happens is whenever you talk of activation functions or sigmoid functions, just forget all the jargons. Just remember that we are talking of making an input bounded. So you have values from, let's say, you know, few of your input data values are from 0 to 5,000. Few of them are from minus 100 to maybe minus 5,000, and a very few values, or maybe even only a couple of values are there from maybe 10,000 plus, something like that. So that makes your data very imbalanced. What we do is when we apply activation function, we are trying to bound our input in some particular range. And there are commonly used functions. So one of the commonly used functions is a sigmoid function, wherein it will try to bound our data with some from some minus to some positive. So minus 6 to plus 6, or minus 1,000 to plus 1,000, that kind of a bounded range. So that our input is, represented uniformly, doesn't have spikes and valleys at, you know, unusual data points. And this mechanism of taking an input and making some prediction is called as feed forward. So I get something, I learn from whatever data was fed to me, then I get some input and I predict something. That is called as feed forward. Now the problem with feed forward is that, where do feed forward networks actually fail? Okay, what are the shortcomings for that? So for feed forward networks, the examples are like when I show a photograph to it, it will label it as maybe a cat or a dog. Okay, again with the use of supervised learning. And since it is supervised, right, every time it makes a mistake, I'm going to step in, correct the error, minimize the error, and then optimize the prediction, optimize the guessing, right? And so whenever a feed forward network is sufficiently trained, it can do a fantastic job. So right now, if you look at all the image recognition or face recognition algorithms which are in the industry, or which are being hosted by the three giants, all of them, we see that they do a fantastic job, almost like a 90-95% accuracy when predicting or recognizing images, faces, right? And the problem with feed forward network is that it just depends on at this point of time. So the photo which is presented to it at this point of time, whether it is a cat or a dog or a fish or whatever, or whether that face belongs to me or to my friend or something like that, what it is concerned is about this point in time, the present moment. It doesn't have any implication, any the notion of order and time, like what if first cat was presented, or maybe a photo of dog was presented, or something of that sort. Doesn't matter. What it actually is concerned about is the input at the present. Okay, which is why we say that feed forward networks are amnesiacs, which means they tend to forget what happened in the past. They don't have a record of the past. It's only about the current present scenario they are interested in, which is why we need recurrent neural networks to have some semblance of some semblance of historic data. So this is almost like same as what we are doing in our feed forward. In feed forward, we used to have input, have some activation function, the output. Now you see a loop here. Okay, so which tells you that at the point t is dependent on the point t minus 1. So it's kind of a network with a value input, some function, it gives an output. It doesn't give actually a direct output. It gives you some what you could say hidden layer, and that is at point t minus 1. That is passed on to t, that is passed on to t plus 1, so on and so forth. Okay, so for example, when we look at the stock prices, right? Stock prices for today are not only I mean, they depend on a lot of factors. They depend on the volume of the stock, the opening value, the previous day's value, the trend of the stock, the stock has been following in the past days, and so on and so forth. It's not only about this point in time. It also has to take into account some past trends. Okay, so this time dependency is achieved via recurrent neural networks. Feed forward neural networks, we I mean to ensure that we overcome their shortcomings, we move on to recurrent neural networks. So this is when we talk of this, unfolding them, this is what happens, that you have an input. Okay, and you have you have an input at t minus 1, and these are the hidden layers, and finally this is the output at time t plus 1. So each neuron is dependent on the prediction of the previous neuron. This is how it keeps a track of what happens back in time. Okay, now RNNs are great when it comes to short context. Okay, so for example, when I speak the sentence, the color of the sky, it's an obvious thing that the color of the sky in most cases will be blue, or something which is related to color of the sky, maybe red, reddish, or pinkish, something like that. But otherwise it doesn't have to remember any previous context, that yesterday the color of the sky was what, or 20 sentences ago the color of the sky was what, and it doesn't depend on that. In most cases that is independent. Okay, but when we are building a story, or when we are constructing automated replies to email messages, or when we are building an image caption generator, or when we are creating poems, in those scenarios, we need our models not only to understand not only to understand the time dependency, but also to remember the context and remember it for a longer period of time, not only for a couple of sentences. Okay, so the thing when it comes to preserving and persisting longer context, and when using the information to generate meaningful information later on in time, at a later point of time, this is where the normal recurrent neural networks, they fail. So if you look at the sentence, right? So I was born in India, then after 10 years I moved to Ireland, where I worked for underprivileged African children, and then after there are a lot of other sentences, and finally I say I speak fluent. Now you imagine that if this sentence, I speak fluent, the output here has to be dependent on so many things. It has to remember that I spoke about being born in India, then afterwards I spoke about moving to Ireland, where I worked for African children. So which means the sentence, the output now is not only dependent on this point of time, it is dependent on some events which have happened in past, and I have to go back, loop back to all those events, get the contextual data, and maybe now make the prediction. Prediction could be multiple, of course. I mean, it could be a series of predictions with the probability. So maybe I speak Hindi, for example, maybe that is the Indian language, could be maybe outputted with a 70% probability. The fact that I work for African children may be outputted with a probability of around 50%, for example. So could be the possibilities, but the important thing to remember is that it has to go back in time and remember all the context. Okay. Again, when it comes to recurrent neural networks, right, why it's not so easy to go back? So what happens is, whenever, I mean, if you remember, when we talked of adding a bias every time, okay, so we talked of inputs, we talked of adding weight to the inputs, we talked of adding bias to the inputs and moving forward. Now every prediction, of course, there will be a certain amount of error there. And now, for let's say now, when we take this sentence, for example, I speak fluent, whatever. Now I have to go back to each layer in the past and then correct the errors there, right? So each sentence I have to go back, correct the errors there, and then arrive to some conclusion. So when we are moving back in time, what happens is that the sigmoid function which we are talking of, right, when for the bounded input. Now when you keep on moving back in time, you can see that the the sigmoid function, because of the nature of the curve and because the nature of the error function, it keeps on diminishing. So by the time you're moving back in time, after that it becomes a straight line. So there are no discernible errors to be corrected. You cannot really apply the error correction to lot of epochs back in time and then arrive at a correct prediction and correct point in time where you are going to make sense of the context. Okay, so this is the problem. So as you go back in time, you kind of lose the context and you cannot find any discernible data point where you can stop and make your conclusions. So this is one of the problems of recurrent neural networks. Okay, so again, recurrent neural networks don't have the understanding of what is important and what is not important information. Which means, for example, I can speak a lot of things and then only some of those things make real sense for my prediction right now at this moment, but they don't have any understanding of what to persist, so how long to persist and what all information to actually carry forward. Okay, so those things are also not very inherent to recurrent neural networks when it comes to persisting information for a longer period of time. Okay, this is where you have long short-term memory, so LSTM. So they have a long short-term memory networks, okay, and they maintain states. So when you talk of context, when you talk of going back in time, back propagation through time, this is where you will deal with states. So you will deal with the states of the input, the output, the prediction. Okay, they can also selectively remember and forget things. When we take a similar stock price analogy, right, the stock price for today will depend on the previous day trends, okay, then the previous day stock price, and also the factors that can affect the stock price today. For example, even though the previous trend was favorable, maybe today there was a political upheaval somewhere in the world that is going to affect my stock price. So even not only the current, the past and the immediate past, so all these things are taken into account by the long short-term memory neural networks. There's also a very interesting comparison for LSTM. So, just to better understand LSTM and how they evolve, let us take a news analogy. So let's say we got a news that there was maybe, a death due to suicide. So all our coverage is hovering around the suicide and what was the victim's mental stage and so on and so forth. Now suddenly, maybe there was a report saying that it was not a suicide, but it could be possibly a murder, right? So now immediately all our stories evolve. Okay, so we totally forget the suicide context and now we are bordering on conspiracy theories, and so we are evolving. So we discarded the previous thing and we are evolving our stories now, and then maybe there is an angle now for some suspect. Okay, so now we discarded our suicide theory. We rebuilt our uh, 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 we rebuilt our story or regarding the murder scenario, and then we added inputs, or we evolved the story or based on some suspects and those kind of things. This is what the LSTM basically does. It will selectively forget things which are no longer essential. So maybe they might have been important at some point of time, but now the narrative has evolved, so it will forget that part. Okay, then it will base its prediction on whatever is the most recent, and whatever most recent, as well as whatever makes sense for the most recent. So now in our news coverage case, we discovered that it was a murder, and there was a new angle for maybe some suspect or some person being involved, right? So now these are our two things for which we are going to concentrate on. This is exactly how the LSTM is going to work. Now, if you look at this architecture, again, all machine learning diagrams and algorithms, I frequently, receive this complaint that they are very overwhelming to look at and understand. But inside, it's absolutely, once you get past the scare for these alpha and tan H and sigmoid and all these functions, I think it's pretty much plain simple English language what we are trying to do. So we will the architecture of LSTM, we will investigate through sports terminology. There's something called as the forget gate. So remember how we said that LSTMs can selectively forget what to carry forward to the next gates. So there is something called as the forget gate. Now imagine that you're just seeing this diagram and you have to understand what a forget gate is. So just imagine this being as a filter function that filters out what information to carry forward. Then come back. So let's say I'm saying Rafael Nadal is a great player. He is, and I absolutely adore him. But Roger is the best ever to play the sport. Okay. So as soon as the subject changes, so from the subject change from Rafael Nadal to Roger, right? Then I realize that Rafael Nadal is not something of interest. The topic has shifted to Roger Federer, right? So as soon as it detects a change of subject, Rafa is forgotten and the subject is replaced by Roger. So forget gate, what it does, it removes the less important, unnecessary or redundant information. And this alpha is nothing but a filter function that filters out the input, and then the filtered input is passed on. The filtered function is passed on. Okay, then we have the input gate. Now in input gate, it decides what to take and what to carry forward. Okay, so when I say that, just look at this sentence. Novak is gluten free. He told me over the phone that he has lactose intolerance too since the last 4 years, right? So important information is gluten free, yes. That he is lactose intolerant, yes. But the fact that he told me over this over the phone is unimportant, right? So I will add new information. So this is an information which I remember, okay, is gluten free. I add new information that he is lactose intolerant, but the information that he communicated this fact to me over the phone and stuff could be overlooked. It could be forgotten. So this is what the input gate does. So input gate, it filters out unimportant information, so which is our alpha filter. Okay, then it also, remember our sigmoid curve where we were talking of bounded inputs. So this is what it does. So the sigmoid function, what it does is it will take all the possible values, okay, that would influence my state and influence my prediction. So it will filter out, it will take previous values, it will filter out the unnecessary ones, it will add new information, and that information it will pass on to the other neurons, to the further neurons. And finally, we have the output gate. Okay. Now, output gate, what it does is, okay. Now, you have to remember that, not at all points of time, our sentence or our text is ready to have some output. Okay. So, not every time it is something like a final end of the statement, and then that could be deemed as an output. That's why we have so many hidden layers. Your input layer, You have hidden layers and you have an output layer. So the output gate basically decides what is the perfect time for me to output. So what is the final thing I'm going to call it as an output, right? So look at these sentences. So Roger Federer is a legend of tennis due to his skills. Okay, for his contributions and elegant, and there's a like a blank there. Okay, so now we have to imagine that our machine learning algorithm has to fill this blank. But there could be a lot of possibilities, like right. So first of all, if you go to NLP rules, I mean natural language processing rules. Now elegant is an adjective. Okay, so strong probability that the blank could be a noun. For example, skill, play, behavior. This is what the output gate does. The output gate, it does the job of selecting useful information and displaying it as an output. Is it an output? No, it requires further processing. Okay, process it further, enhance it further, filter out or add new information. Now is it an output? Still no, enhance it further. So this is what the output gate does. It decides when to display something as the final output, or does it require more pre-processing. Okay, so the output gate, if you look at this, what it does is this is the filter function. This is where it will take into account the activation function. Activation function is combining the inputs and multiplying them by weights and stuff like that. Okay, and it also, what it does is, if there are multiple outputs, okay, so as I was saying, if there are multiple outputs in the case of the previous example where we were talking of language fluency, then it will diminish the others in comparison to one particular value, and then that value will be kind of highlighted, given a more weightage, and passed on or displayed as the final output, whatever is the scenario. Okay, so these are the three gates: forget gate, input gate, output gate, on which our long short-term memory works. All right. Okay, now before we move on to the actual coding demo, I want you to have a look at one of the auto poem generators, for example, right? So okay, let us go back here. So this is, yeah, so this is the website. Okay, I have shared it on my screen also. Yeah, all these websites, what they do is they pick up one particular poem. Okay, or sorry, not poem, they pick up one particular poet. For example, Rudyard Kipling, or W.B. Keats, or Thomas Hardy. So all of these authors or poets, they will take their renowned text, they will train their machine learning algorithm on one of these classic text. Okay, even Shakespearean, for example, for that matter, like for Macbeth, for example. So you will find that most of the story generators or play generators that you have online, they will base their training on a set of the classical data which is available, classical text which are available, and then the LSTM will kind of comprehend it, and then given one particular sentence, which what we called as the random seed. Okay, some random text which is given, it will output some meaningful sentence. Again, as we will see in our coding demo shortly, that not all of the sentences are going to make sense. This is where your supervised learning comes in, but at least they are grammatically correct. Okay, with making almost like 70% of sense. So this is a poem generator in which it has ingested, I think, poems from a lot of best-selling poets, a lot of famous poets. And so let's select a tone for our poem. It is going to be happy, sad, or angry. So maybe let us say sad. Okay, no, let's keep it happy. Okay, the gender person is about, let's say, female. Okay, and then I can input anything, something belonging to that person. So maybe I'll put hair. Okay, for example, since it's a female, maybe long, shiny, blonde, then what else? Okay, let us stop here. Okay, some adjectives to define, maybe curly, maybe wavy. Okay, something of that sort, right? And then write me a poem. Okay, this is how your poem will be generated. Whose hair is that? I think I know. Okay, the owner is quite happy though. Blah, blah, blah. Okay, now if you look at this, the hair is long, shiny, blonde, curly, wavy, and deep. Okay, but she has promises to keep. If you look at this text carefully, and if you have been in any way a Rudyard Kipling fan, this is a Rudyard Kipling poem. The woods are lovely, dark and deep. I have many promises to keep. So you just see that, you know, how it has taken up our adjectives and blended it with the text which it has ingested, and then come out with something coherent. You cannot really discard this as an inconsistent or incomprehensible text. It is quite coherent, it is grammatically correct, it has a decent rhyme scheme also, right? So shake, break, aches, awake, deep, keep. Okay, so yeah, I mean, and the entire poem sort of yes, it has it with thanks to the poet Robert Frost for the underlying structure, right? So this is a total fake poem site where even, you know, the comments and voting are generated by the AI. So auto praise, so even the praise is auto praise for the long, shiny, blonde, wavy, curly hair. The title of the poem is auto generated. All right. So I mean, yeah, endless possibilities. As we saw the Toyota ad campaign, we saw this poem generator. There is a horror story generator. Okay, I would like to point you to a very interesting source here, where, you know, around 30 hours of testing has been gone here, and this is a comprehensive poetry database. All right. And this is a pre-trained. If you want to, I mean, input your own text, you're most welcome to do that. But this is a pre-trained, so you will just use a generate.python file here, generate.python file, and use the input data which is already pre-fed, pre-trained. Okay, and then you just give a seed text here. So here, you know, input text is a butterfly in, and then it is actually going to give you a lot of a entire poem with starting with a butterfly in the sun and something, or maybe not rhyming, you know, maybe a prose most of the times. But yeah, I mean, it can give you a lot of possibilities also. So maybe you don't like this version, you can try another version. So maybe generate again, and it will give you another uh, decent looking poem. Okay, supposedly written in some influence style by the Robert Frost or Rudyard Kipling or something of that sort, right? And finally, let us come to our project. There's also an ongoing project which I am also contributing on. It is for horror story generation. So we are collating texts of all horror story writers like H.P. Lovecraft and Stephen King and Neil Gaiman, and then, you know, coming out with some gory text, or, you know, some equally chilling stories, short stories, one liners, for example. Yeah, so endless possibilities, absolutely endless possibilities. Let us come to our demo. So for our demo, I am using a hotel text generation. Okay, so uh, when you go on Agoda, right, you have a lot of hotel reviews. For example, if you look at, for example, one particular, let's say, hotel in Bali, then you will have an overview of that saying located at a serene place, away from the city, in the lush greenery of XYZ, and only 2 minutes walk from the beach and stuff like that. So here, for our demo purpose, we collated reviews from around 150 hotels, okay, in Seattle, okay, and we are training our algorithm on those data. And then once and given seed text, we will see that, you know, how it is outputting. For LSTM, we need to use something called as Keras. Okay, Keras is an abstraction over TensorFlow. And if you really want to code using your own notebooks, I mean Jupyter notebooks, or on local environments, then Keras and TensorFlow can take, especially on Windows platform, Keras and TensorFlow can, you know, really eat up a lot of time being set up. So instead, you know, now as is the trend, you can actually use Google Colabs or Azure Notebooks. these are Jupyter notebooks in the cloud platform. So they already, the libraries which you need not actually pip install or conda install them locally on your machine. You can just call whatever imports you want, and those imports will be sourced directly from the cloud. Of course, for Azure, you need to have your own account. For Google, I think Google Drive, if you have Gmail account, the collabs are linked with your Google Drive. For Azure notebooks, they are already linked with your GitHub account. So yeah, so and they give you the exact same interface. So this is not a Jupyter notebook. This is actually a Azure notebook. If you see azure.com, this is an Azure notebook, a Jupyter interface running in the cloud, where I have not even installed a single library, and I am still being able to use the NumPy, Pandas, Keras, and TensorFlow and those things, right? So I'll just quickly show you my input data. My input data looks something like this. Sorry. Okay, LSTM. Okay. My input data is just the name of the hotels and a description about those hotels. Okay. And so if you look at the name, okay, the address and the description of the hotel, like located on the southern tip of Lake Union and so on and so forth, right? So we are taking all this data and we are training it. Actually, when you look at all the theory behind LSTM, and when you actually look at the code, what we are writing in our notebooks, that is pretty simple. So you are taking in our hotels.csv file. Okay, this is one of the sample description how it looks like. Okay, then we are tokenizing. Doing some NLP things. For example, all of the words you are going to tokenize them. Then you are going to lemmatize them, meaning playing, play. Going, gone, went. All will revert back to it, the root word go. So lemmatization, tokenization. Okay. Then we are constructing. TFI, a document frequency, inverted frequency, wherein each word, for example, located has been allocated some numeric equivalent. Okay, depending on the frequency of its usage, depending on the position where it is occurring, and all those things. We are creating a sort of numerical representation for each of the words in our data set, in our input data set. Okay, and then for example, when you take the first 10 words, this is how the numeric representation is going to look like. So these are actually words, located in mountains, located in the mountains near to something something. So this is nothing but these are actual words represented as your numbers, numeric data, right? Okay, so now finally you are going to create our feed. So you're going to take the hotel descriptions one by one. You're going to feed it to our TensorFlow Keras model, right? So this is our model. Okay, and we are going to train now when we talk of neural network side, we have to tell the neural network how many hidden layers are going to be there. So we are going to have over 100 hidden layers. There are certain industry standards for that. Then we are going to have a dropout for each level. Okay, dropout meaning roughly how much information to ignore. Okay, so LSTM it itself also will perform filtering of information, but dropout at each of the stage we are showing here, we are configuring here. Okay, and these are some of the optimizer functions. These are again industry standards. Okay, so whenever you are now your model is created now. So your model is created. Once your model is created, now you're going to train the model. We are training the model for 100 epochs. As you can see, I have started training it at maybe morning 11 o'clock, and at around 7 o'clock it is still at only 8 epochs. Okay, so you can imagine, because the for LSTM and all these things with humongous text, you need GPUs or TPUs. I'm operating with CPUs and that also with a lot of other shared programs. So, you know, it will take around 5-6 hours even for small data to be trained and for us to give accurate predictions. If you just want to play around and, you know, arrive at some conclusion quickly, you can give epochs for 20. 20 is the minimum industry standard. You need to train your data at least for 20 epochs. Epochs meaning iterations, right? So I'm training for 100 iterations, and then finally, you know, I will give some random text to it. Okay, and this is where I'm going to, this generate text is going to generate my prediction given an input text. Okay, so I'm just giving some sample input text. It's Hilton, Seattle, downtown, right? And I want to generate at least 100 next words after Hilton, Seattle, downtown. I want to generate the next 100 words of description, next 200 words, next 300 words. And if you look at the output given by our model, okay, so now Hilton, Seattle, downtown is located in the heart of downtown Seattle. Fantastic sentence. The waterfront inn. Now it, you know, it actually changed the subject. We are talking of Hilton, Seattle, downtown. But anyways, the waterfront inn is a contemporary heaven near hotel at L something something, with the simple food of featured with the large inviting of featured in the quiet gym sound. Okay, so you see that not all the words they make sense. You know, for example, simple food of featured or inviting of featured. But this is what, you know, you have to keep on correcting. But at least it is not how should I say? It is not incoherent or it is not grammatically incorrect, and it has all the keywords which we are looking for, like contemporary or quiet or local views or heart of downtown, right? And as and when you train it better or feed it more data, so next time you try to feed 200 inputs, okay, or 500 inputs, and then train it for around 150 epochs, your accuracy is going to increase. Or when you're outputting even more text, so for 100 text, it made a decent job. For 200 words, maybe it is going to make more sense, have more information, have more grammatical consistency, have more coherent reading, right? So yeah, I mean, this is what LSTMs are capable of doing. So as you can see that, you know, for 300 words, it has done a good job. I mean, it has covered a lot of features. It has covered about the hotel descriptions, the room, the proximity to local markets and stuff like that. So yeah, I mean, you know, you can get a sense of with little code, we have managed to achieve a lot. I mean, the stuff which we are doing here is nothing but, you know, just outputting words as numbers. The crux, the core work we are doing here is only here, where we are feeding the words to our model, creating the model, and then predicting the text, given some input, given some random text. So yeah, that's about it. You know, as I was telling, the applications of LSTM are endless and quite interesting, quite variegated, and sky is the limit for our imagination. We are happy to play around with the code and happy to let your imagination run wild.
All right, thank
Any
you so
question?
much. Yes, let's take another maybe 5 minutes or so and do a quick Q&A. There's a question from Shweta in the chat, and she says that you skipped memory gate. So you want to talk about that quickly, Priyanka?
Sure.
In the meantime, if you have any other questions, feel free to either unmute or drop them in the chat here.
Just a second. Okay, so you had the forget gate. Yes, you had the, sorry, I need to minimize. Yeah, you had the input gate. You had the output gate. Yep.
Shweta, do you want to unmute and add a little more
Yeah,
context to the question?
yes.
Do we have Shweta on the call here? Okay, I'm going to take that as an unwillingness to share more context. So let's move on. Anybody else have a question for Priyanka? Feel free to unmute. If you want to add something, please go ahead. We still have a little bit of time.
Actually, when Shweta, you talk of memory gate, right? Memory gate is almost like, you know what, it is almost similar to back propagation in time, which is what it is done by the input gate only. So input gate is actually, if you see that, it is a combination. It remembers as well as propagates. So if you talk of memorization through gates, this is what it is going to be. So input gate is a combination of lot of things. Sigmoid filtering functions, activation functions, remembering, carrying on, carrying further. So yeah, I mean, that is if that is what you are pointing at.
Cool. Thanks for addressing that, Priyanka. We have one more, and the question is, what would be the difference between using LSTM for sequence generation and LSTM for binary classification?
Yeah, actually, see, LSTMs for binary classification could be, you know, content filtering, content classification can also be done. But the thing is, for a task which is as simple as binary classification, why do you want to indulge in neural networks? There are linear regression techniques, there are other simple techniques, and which are going to give you good accuracy also without delving into the complexity of neural networks and without delving into the complexity of keeping into account you know, time series and all these things. So LSTM is basically when you have time series data, time related data. For binary classification, unless and until you have complex data that would, you know, want to be categorized as per time. So today something which is categorized as a deadly virus tomorrow might not be a deadly virus, right? Then it makes sense to use LSTM for those kind of scenarios. But otherwise, if you want to just categorize patients as healthy or non-healthy, or tumors as malignant or benign, or you know, cases as positive or negative, I think your normal regression, linear regression, and other algorithms are going to do a decent enough job. Again, add to it the complexity of having to set up tensor and TensorFlow and Keras and other supporting libraries for LSTMs. I mean, your linear regression libraries are much straightforward, right?
Cool. Thanks, Priyanka. We'll pause the Q&A here for now. We will continue, or we can continue on Slack. The link is in the chat, in the Zoom chat. We will also post the link on the meetup page so that you have that. We'll drop a link to the Slack channel and to the specific channels that you can join. Priyanka will be available to answer questions on Slack for the next week or so. Feel free to drop in, feel free to chat, feel free to ask any questions that you might have. And please join the Singapore channel on Slack to talk more about Singapore and women who code in Singapore in general. Again, thank you so much, Priyanka, for taking the time to talk to us about LSTM. Thank you everyone who joined us on this workday evening. I have dropped a link in the Zoom chat, which is a link to a feedback form. Please help us to fill the feedback form. It'll help us improve the future events we do, address any concerns you might have, and also encourage us to keep going. We really, really appreciate your feedback. With that, just final words. Our next event is on Friday. We're going to be having an informal online chat. Please join us, talk to us. And I have a question here asking if there will be a recording. Yes, there will be a recording of today's session. It will be available on the Women Who Code YouTube channel and the engineers.sg channel. So you'll have access to it in 2 places. We will drop that link also on the Meetup page once it's available. And with that, that is it. Again, a big thank you to everyone. Stay safe.
Thank you all. Thank you so much.
Thank you, Priyanka. Thanks, Purnima, for hosting.
This is awesome. Thanks, everyone.
That is it from us. Thanks, everyone.
Bye-bye.
Good day. Bye-bye.
Bye-bye.